In this video, we are going to talk about dimensions of physical quantities. What exactly is dimension? Dimension of a physical quantity is the index or power of each of the fundamental quantity. What are the fundamental quantity we are talking about? That is length, mass, time, temperature, luminous intensity, current, and amount of substance. Now, in video 1, we've talked about physical quantities and units, so you can watch the video 1 again. Now, which expresses that quantity, full stop. So look at this, everything here. Dimension of a physical quantity is the index or power of each of the fundamental quantity. So all this now, they are the fundamental quantity which expresses that quantity. So now let's understand this definition so we can really understand what is dimension. So let's break it down one by one. Dimension of a physical quantity is the index or power of each of the fundamental quantity. Length, mass. For example, let's take velocity or speed Now, what is speed? Let me use speed first as example. So what is speed? Speed is equals to distance. Speed is equals to distance over time. Now, you know that distance is a kind of length. So that means distance can be length divided by time. So speed is distance over time. That means speed is length over time. Now we will use length, represent length as capital L and represent time as capital T. Use their initial. So length use capital L, time use capital T. Now in indices, this is the same thing as L times 1 over T, because this is over 1. So that L times 1 will give you L. 1 times T will still give you T. So that means L over T is the same thing as L times 1 over T. And in indices, we can have 1 over A is equals to A raised to power minus 1. That means 1 over T is T raised to power minus 1. So that means this combined is LT raised to power minus 1. That means this will give us the dimension for speed. Now let's use this to divide the dimension again. Remember, this L can be power 1. That is L raised to power 1, T raised to power minus 1. So it's the same thing as this. So now let's go back to the definition. So dimension of a physical quantity is the index or power on each of the fundamental quantity which expresses that quantity. Here, the fundamental quantity that expresses speed here is length and time. That means mass did not play any role here. Temperature did not play any role here. Luminous intensity does not play any role here. Current does not play any role here. Amount of substance does not play any role here. The only one that we use here is length and time. That means it's only length and time that expresses speed. Now, dimension of a physical quantity is the index or power of each of the fundamental quantities. So any one of length, mass, time, temperature. But here, these are the powers. So dimension of a physical quantity is the index or power. So that means 1 here is index or power. This one too is index or power, which expresses that quantity. The one that expresses the quantity is length and time out of all this. Now, the meaning of this is that mass is not really important in defining speed. The only one that we need is length and time. That means mass has dimension of 0 in the dimension of speed. So that is the main definition of dimension. Dimension is the index or power of each of the fundamental quantity, any one of these, which expresses that quantity. So the one that expresses it here is length and time. So that is definition of dimension. So let us now see points here. Now in dimension, there are some things you need to know. First, you need to know that height, as in height, width, radius, let's say displacements, or distance are types of lengths, meaning height, width, radius, displacement, or distance are types of lengths, and we represent its dimension. So height, width, radius, displacement, or distance are types of length, so we represent their dimension as capital L. So that means in dimension, anytime you say height, width, radius, displacement, or distance, use it as L, represent the dimension as L. So there are types of lengths. So now let's take area for example to explain something there. Area is equal to length times width. So this is formula for area. Area is length times width. Now look at this. Length is L. Width, look at it, and I said width is also a kind of length. So that means width is also L. So that means L times L is L square. So that means we can say the dimension of area, so you use this bracket, the dimension of area is equals to L square. So dimension of area is equals to L square. Take notes. So now, what of volume? If I want to talk about volume, what will be the dimension for volume? So I'm trying to explain width, length, distance, displacement, radius, so you can know their kind of length. So now let's talk about volume, and jot all this, we will need them later. So volume, what is volume? Length, formula for volume is length times width times height. So volume is equals to length is L times width. Now check, width is also a kind of length. I said anytime you see it, use L. So it's still L times height. Height is also a kind of length. Look at it here. We still use L. It's a kind of length, so it's still L. So anytime you see them in dimension, use L. So volume now is equals to L raised to power 3. That is L raised to power 1 times L raised to power 1 times L raised to power 1. That means we have L raised to power 3. That means the dimension of volume, we use the bracket to represent dimension, is L raised to power 3. So that is the dimension of volume. So again, if the dimension involves time, We will now represent it as capital T. If the dimension involve mass, we will now represent it as capital M. We are using their initial. Time, capital T, mass, capital M. If the dimension involve temperature, if the dimension involve temperature, we are going to use, you can use K for temperature. If the dimension involve currents, if the dimension involve currents, you can represent it as A, amps, the unit. So now, that means all these fundamental quantities, length, mass, time, temperature, luminous intensity, current, amount of substance, can play a role in our dimension. And anytime you see them, use their initial to represent their value, their dimension. So we use their first letter to represent their dimension. But temperature, since we have time before as T, I don't want to use temperature again as T, so I use K. Current, we can just use A. While some we use I. It depends. So now let's go into the dimension fully now. So let's start with dimension of force. What is the dimension of force? So you have to break everything down in total. So now before we take force, let us do we've done speed, right? We said speed is display and distance over time. Likewise, if I do for velocity, what is the dimension of velocity? Velocity is displacement over time. That means dimension for velocity is equals to, now we've already said that displacement is a kind of length, so that means I'm using L divided by time, I'm using T. Check again. So that means dimension for velocity is equals to LT raised to power minus 1. So that is the dimension of velocity. Now what is now the meaning of this LT raised to power minus 1? So everything here, this is called dimensional formula of velocity. So if I say what is the dimensional formula of velocity, you will tell me LT raised to power minus 1. Now in this case, velocity we have, this is power 1. Velocity we have one dimension in length, one minus 1 dimension in time. As you can see, we have said dimension is the index or power of each of the fundamental quantity that expresses which expresses that quantity. Now the index that expresses the quantity length here is 1. That means L raised to power 1 is 1 that expresses the quantity length. So that means 1 dimension in length. Velocity has 1 dimension in length. The quantity that expresses time here is minus 1 as the index. The index that expresses the quantity t here is minus 1 rather. That means velocity will have minus 1 dimension in time. That's why dimension is the index or power of each of the fundamental quantity which expresses that quantity. So all those power are called dimension. So that means velocity will have 1 dimension in length, minus 1 dimension in time, and zero dimension in mass. Zero dimension in mass, meaning there is no mass here. This is the same thing as m raised to power 0, L raised to power 1, T raised to power minus 1. So zero dimension in mass. Not only mass, zero dimension in temperature. No temperature. Zero dimension in luminous intensity. Zero dimension in current. Zero dimension in amount of substance. So that is what we have in dimension of length. That means in dimension of length, we only define it with length and time. There is nothing like mass, temperature, etc. So, MLT, notes, ML, T raised to power, L T raised to power minus 1 is called the dimensional formula for for velocity, and also the powers are also called dimensions. So you should be able to understand the definition of dimension better now. They are the power of or index of each of the fundamental quantity which expresses that power. So which expresses that quantity. So let's proceed. Let's take another dimension. Let's say momentum. What is the dimension of momentum? Before you can do dimension, you must know what is the definition of that quantity. Quantity momentum now is what? Mass times velocity. Momentum is mass times velocity. Now, what is now the dimension for momentum? Momentum, m mass, so we use capital M for mass, times velocity. We have done velocity now. That is LT raised to power minus 1. Check again. I've told you that dimension for velocity is LT raised to power minus 1. You can backward the video. So that means we now have what? ML T raised to power minus 1. So that means the dimensional formula for momentum is ml T raised to power minus 1. Why in momentum? Momentum will have one dimension. Momentum will have one dimension in mass. One dimension like their power 1 here. One dimension in length minus one dimension in time. So where everything together is called dimensional formula, why their powers are called dimension. So like that. Now let's take acceleration. What is the dimension for acceleration? We know that acceleration is equals to velocity over time, as in change in velocity over change in time. So if initial velocity is 0, so acceleration will be velocity over time. So now we have done velocity. So acceleration is equals to velocity is LT raised to power minus 1. Note it now. So we have done velocity times 1 over t, because this time now, or you can simply say the one you will understand, the up one is velocity LT raised to power minus 1 divided by time, as in t. So now this is over 1. Anytime division change to times, we are going to have LT raised to power minus 1 times T raised to power minus 1. If you change this, it will be 1 over t. So So anytime the division change to times, that will be 1 over t. And what is 1 over t? This will be lt raised to power minus 1 times t raised to power minus 1. You change this. So that will be lt raised to power minus 2. In law of indices, you add the power. Minus 1 is minus 2. That means the dimension for acceleration is lt raised to power minus 2. Notes. So that is the dimension for acceleration. Now, let's take another one. Let's say the dimension for force. Force. What is the dimension of force? Force is mass times acceleration. That is the formula for force. But now, what is the dimension for force? We already know that mass will be capital M times now acceleration. We have done the dimension of acceleration now, and that is dimension of acceleration. We have done it. That is lt raised to power minus 2. Please check. That means the dimension for force now is ml t raised to power minus 2. That is the dimension of force. So before you can know the dimension of physical quantity, you should know the formula first. Now, master all this. So you need to know dimension of force often for JAM or objective exam. Force is ml t raised to power minus 2. We'll be using it time to time now. So let's do another dimension. Let's say, what is the dimension for work? Work is force times displacement. And we know the dimension of force now. That is ml t raised to power minus 2 times displacement is a kind of length, so that will be L. So dimension of work or energy. So if you say energy, you take it as work. Dimension of force or energy is ml square t raised to power minus 2, as in L times L square t raised to power minus 2. So because the power of L here is 1, power here is 1, add it together, that will be 2. So that means this is the dimension of work. What is the dimension of power? Power. Now, power is work done over time. So we know the dimension of work already. That is ml square t raised to power minus 2 divided by time, which is t. So that means this is the same thing as ml square t raised to power minus 2 times t raised to power minus 1. Because this is over t, it can become t raised to power minus 1. So that means this is ml square t raised to power minus 3. So minus 2 minus 1 is minus 3. That means the dimension for power is ml square t raised to power minus 3. So like that. So now all this dimension we are doing one by one. So you just have to master it. So and what is the meaning of the dimension? This is dimensional formula for work. It means in work done. Work done has 1 dimension in mass, 2 dimension in length, and minus 2 dimension in time, 0 dimension in temperature, 0 dimension in current, etc. Also, power we have 1 dimension in mass, 2 dimension in length, minus 3 dimension in time. That's the meaning of all this dimension here. So the next thing, let's do for pressure. What is pressure? Pressure is force over area. So let's do the dimension for pressure. Can jot everything and note it. So dimension for pressure. Pressure is force over area. So you have to know the formula. So pressure is equal to, what is the dimension for force? That will be ml square force ml t raised to power minus 2. We've done force, you can check again, over area. Area is a kind of length, that will be L square, L times L, so that will be L square. So that means pressure, the one L will cancel out, it will be ml raised to power minus 1 t raised to power minus 2. So that means let's use P for pressure. So that means the dimension for pressure, dimensional formula for pressure is this. And pressure has one dimension in mass, minus one dimension in length, minus two dimension in time, zero dimension in other quantity. Now let's say the dimension for area of a circle. Now let's say find the dimension for area of a circle. So dimension of area of a circle. First, what is area of a circle? Area of a circle, area of a circle is equal to pi r square. Now, what is the dimension for area of circle now? Pi r square. So area, pi is a constant here. Leave it as pi. So dimension of area is pi times dimension of radius, that will be dimension of r square. So now dimension of area, anytime you have a constant or anyone that is not part of your physical fundamental quantity. What are the fundamental quantity? Length, time, mass, luminous intensity, current, amount of substance, etc. They are fundamental quantities. Anyone that is not there is constant. For example, pi is constant here. I've told you that radius is a kind of length from beginning. That means if pi is constant, change it to 1. That means dimension of any constant is 1. Take notes. Times radius will now be L. That will be L square. That means dimension for area of a circle is L square. So dimension of area is still L square, like that. So you will now notice now that pi is not a kind of length or mass or time or any of the fundamental quantity. So pi shouldn't affect the dimension of area. That means pi will just change to 1 because it's a constant in that sense. Take note. So now the dimension of pi, if you want to write it now, should be like 1, as in dimension of pi is 1, is a constant, is none of those physical quantities, which is m raised to power 0, l raised to power 0, t raised to power 0. That means pi will have 0 dimension in mass, 0 dimension in length, 0 dimension in time, 0 dimension in temperature, 0 dimension in current, as in like that, is constant. We only write the first 3 here. Anyone that surface again will write it, but we are just using mass, length and time. They should be all the 7 fundamental quantity, but we don't need to be writing everything at the same time. So now we can say that pi is dimensionless. Now we can say pi is dimensionless, meaning it does not have any dimension. Now with similar logic, now any number, as in ordinary number, any number is dimensionless. That means dimension of 200, dimension of -1, dimension of 3, dimension of -1/2, dimension of 10 over 7. So dimension of any number is 1. That means they are dimensionless. They don't have any dimension. So that means their dimension is 1. That is m raised to power 0, l raised to power 0, t raised to power 0. So note these ones, they are important too. Dimension of pi is dimensionless. Any number at all, dimension is also dimensionless, meaning they don't have any dimension here. Now, what is the dimension of volume again? I want to explain something there. So what is the dimension of volume? Dimension of volume. We already know that volume is length times width times height. So that will be length times width times height. So dimension of volume now. Length, we've done volume before, so I'm just doing it again. Length is a length. Width is a kind of length. Height is a kind of length. So that means the dimension for volume is equals to L raised to power 3. So take note. Now, what is the dimension of a sphere, or dimension of volume of a sphere? Now, for a sphere now, for a sphere, volume, what is the volume of a sphere? Volume is 4 over 3 pi r cube. This is volume of a sphere. Now, what is the dimension of this? Dimension here will be dimension of volume for a sphere is equals to, this is a number, and I told you dimension for any number, like dimension of 4 over 3 times dimension of pi times dimension of r raised to power 3. So that means dimension here is, I've told you now that for any number the dimension is 1. Likewise pi is also 1. Now r radius is a kind of length. Now I've told you that radius is also a kind of length, so we use L. That means the dimension of volume is equals to L raised to power 3. That is for volume of a sphere. Compare these two results. You will see it's the same. Volume and volume of a sphere. So dimension of volume will always be L raised to power 3. Dimension of volume will always be L raised to power 3, whether it is volume of a cuboid or volume of a sphere. Volume of anything, it is always L raised to power 3. That means dimension of a physical quantity will be the same, and it does not depend on which formula we are using for that quantity. Formula can vary, but the dimension will remain the same. That's what we're trying to say. Find the volume of anything. Dimension is always L raised to power 3. Please take notes of that. So now, let us see dimension of angular quantity. Dimensions of angular quantity. Dimensions of angular quantity. So I can clear the definition of dimension, but let me still leave it. So let's take dimension dimensions of angular quantity. Dimension of angular quantities now. So what are the angular quantities? Let's start with theta 1. Angle theta. Now Theta is called angular displacement. Angular displacement. Angular displacement, we represent it as theta, and the formula is arc over radius. Angular displacement is arc over radius. So that means the dimension here, dimension of theta, so angle theta will be, arc is a kind of length because this is an arc, so and is a length, divided by radius is also a kind of length. So that means length will cancel out length. So dimension of theta is equals to 1. Now, this simply means is dimensionless. That means theta is dimensionless. So if I say find the dimension of angle theta, dimension of angle theta is dimensionless. Take note. Now let's say another one. The first one we talk about is angle. Now let's see another one. Another one is angular velocity. So that theta is angular displacement. Now what is the dimension of angular velocity? Dimension of angular velocity. Angular velocity is omega. That symbol is omega. And angular velocity is theta over time. Now, in the comment box, you can ask for formulas under physical quantities. So I can send like 77 formulas under physical quantities. Or you can chat this number on WhatsApp 070 461 88392. You can chat me on WhatsApp here. I will send you the formulas for physical quantities so you can be using it to do your dimension. So let's proceed. Now, the next one is angular velocity is theta over time. You can always use the comment box too in case the number is not available. Use the comment box. So angular velocity over time. We have already shown now that the dimension of theta is 1, meaning is dimensionless. So is 1. So that will be 1 divided by dimension for time is t. So that means dimension for angular velocity is equals to t raised to power minus 1. So meaning it's also all those ones that is not there, m raised to power 0, l raised to power 0, t raised to power minus 1 is the same because anything raised to power 0 is 1. That means the dimension for omega angular velocity is t raised to power minus 1, meaning it is 0 dimension in mass, 0 dimension in length, minus 1 dimension in time, 0 dimension in current, 0 dimension in temperature, like that. Now another angular quantity is angular acceleration. So take note of all these angular. So angular velocity is t raised to power minus 1. Now let's say angular acceleration. Angular acceleration. We use alpha to represent angular acceleration, and is change in angular velocity over change in time. So that means angular velocity is equals to change in angular velocity. We have known angular velocity now. That is L, and that is t raised to power minus 1 divided by time also t. So this one will become t raised to power minus 1 divided by t, as in I can say divided by t, which is also t raised to power minus 1 times, we can, this is t raised to power 1, though that will now be times 1 over t. because this is t over 1. So and what is 1 over t? That will be t raised to power minus 1 times t raised to power minus 1. That will be t raised to power minus 2. That means the dimension of angular acceleration is t raised to power minus 2. Or you can simply say m raised to power 0, l raised to power 0, t raised to power minus 2. So like that. Now let's talk about torque also. What is the dimension for torque? Dimension for torque. So torque now is force times arm length. Now torque is t. I will use t. It's a kind of force. So force times arm length. We have already know the dimension for force. It is ml t raised to power minus 2 times dimension. Arm length is just l, so that will be l. So dimension for torque now is ml square t raised to power minus 2. That means torque will have one dimension in mass, two dimension in length, minus two dimension in time. So now let's say dimension of physical constants. Another one, dimension of physical constants. Dimensions of physical constants. Dimension of physical constants. So let's take gravitational constants. Now gravitational constants, we represent it as capital G. Now if two bodies of mass m1 and m2 are placed at a distance r, both feels gravitational force whose value is, so let me clear this. So we place two objects at distance r, they will feel a gravitational force of g m1 m2 divided by r square. So now if you cross multiply here, so we are looking for g. Let's make g subject's formula. This will be g m1 m2 is equals to fg r square. So that means g is equals to gravitational the force, gravitational force is equals to fgr square over m1 m2. So that means the dimension of gravitational constants. Now we have known force already. We have found force before. That is ml t raised to power minus 2 times radius is a kind of length, so that will be r square, that will be l square divided by mass, that will be m times m, that will be mass. So 1m will cancel out, so it will remain 1m below. So gravitational constants will be m raised to power minus 1, because m here 1, it remain 1m. Then l raised to power 3, because this is l square and this is power 1. Then t raised to power minus 2. Now this is the dimension of gravitational constants. Take note. So now let's say dimension of specific heat capacity. Dimension of specific heat capacity. To increase the temperature of a body, by delta T. Heat required is Q is equals to mc dt, where your C is the specific heat capacity, m is the mass, while the T is change in temperature. At least you can see there is now temperature here. So that means dimension of Q will be equals to m, that is m, capital M. C is specific heat capacity. And what is the specific heat capacity? S. So we'll use S for it. Then is the one we are looking for. Yeah. So I said find the dimension of specific heat capacity. So we are starting with Q is equals to mc theta. Q is quantity of it, m is mass, C is specific heat capacity. Find C here. C will be Q over m change in temperature, as in divide both sides by m change in temperature, so that we can find C. So now what is C? The dimension of C, specific heat capacity, is dimension of Q divided by, now Q is a kind of energy, so dimension of m, dimension of the thing. So Q is quantity of heat, so and is a kind of energy, and I told you the dimension for work done is still the same dimension for energy. We have done work done before, that is m L square T raised to power minus 2. You can check again. So divided by m K. Now I'm using K because I have temperature now. So I'm using K for temperature. You see it's part of fundamental now. Every time is not MLT, any of the fundamental quantity. So mass will cancel out. That means dimension of specific heat capacity is L square T raised to power minus 2 K raised to power minus 1. So that is it. You will see that m is missing. So I can say the dimension of specific heat capacity is m raised to power 0 L square T raised to power minus 2 K raised to power minus 1. That means specific heat capacity, the dimensional formula is this. And it will have 0 dimension in mass, 2 dimension in length, minus 2 dimension in time, and minus 1 dimension in temperature, but 0 dimension in amount of substance, 0 dimension in luminous intensity, like that. So 0 dimension in current, like that. So that is dimension of specific heat capacity. Now let's do another one. Let's say the dimension of, you can comment in the comment box to ask for the formula, so I'll give you a question. We are going to do different dimensions. So now let's see another aspect now. So what is dimension of coefficient of viscosity? Let's discuss that one too. What is the dimension of coefficient of viscosity? Coefficient of viscosity. What's the dimension? Coefficient of viscosity, Fv, is equals to 6 pi rho Rv. So that is the coefficient of viscosity. So that means if any spherical ball of radius r moves with velocity v in a viscous liquid, then viscous force acting on it is given by this formula. Then that is coefficient of viscosity here. So now to find the dimension of coefficient of viscosity, so we need to divide from here. Now you will need to say coefficient of viscosity is the force acting on the force acting on it divided by 6 by rv. It's like you are dividing both sides by 6 by rv so that it will cancel out. We'll have only this. That means in the coefficient of viscosity here, so the dimension will be equals to, we've done force ml t raised to power minus 2, you can know it offhand, divided by 6 will be 1, no is a constant, is number, pi is also 1, radius is length, and volume is L raised to power 3. 1 L will cancel out. That means coefficient of viscosity is equals to ml raised to power minus 3 c raised to power minus 2. So that is the dimension of coefficient of viscosity. Now, oh, it remains one. This is not volume, this is velocity. Sorry. So I need to change that. So velocity, not volume. This is velocity. Coefficient of this, and we've done velocity lt raised to power minus 1. So that means coefficient of viscosity is m L raised to power minus 1 t raised to power minus 1. You know, we have t raised to power minus 2 to be plus 1. This one will go up and becomes plus 1. Law of indices. That means the coefficient of viscosity is, the dimension is ml raised to power minus 1 t raised to power minus 1. So now the remaining part is we need to do some special features of dimensions. Now this part is interesting. I'll do that in another video, so you can watch the video. In the next video we will see dimension, that is, we'll talk about some special features of dimension. This part is very important, so watch that in the next video. Thank you.